From now on, the lesson is recorded. Okay, so now let's take it from the beginning. The first topic was about infinite sets and finite sets. Here you must be able to recognize, to know the definitions first of all, and to recognize countable and uncountable sets. For example, if I take the set A equals the set of all those numbers of the type a square and root of n squared plus 4 over n plus 2, when n it's a natural number. Question, is it countable or uncountable? This could be a question at the partial. Okay, what's your answer? And then we must somehow prove that answer. Is it countable or not? Of course, we must know what a countable set means. And what is a countable set? A set X is said to be countable if and only if. What's the definition? We must know the definition. If we don't know in general, if we don't know the definitions, we cannot solve exercises because the notions must be known. What is a countable set? It is equipotent with a set of natural numbers. So this is the definition. What it means to be equipotent? It means to exist a function f from x to n or from n to x, a bijective function. Or in other terms, one-to-one. This is how we call it. A one-to-one map from the set x to the set n, or conversely from n to x, of course. So in our example here, A, is it countable or not? Or of course, we must know some basic examples from the lecture of countable sets. For example, the set of natural numbers, it's of course, according to the definition, countable. But also we have proved that the set of integers is countable. And also at the lecture, we proved that the set of rational numbers is countable too. So we have 3 basic examples of countable sets. Okay. Starting from here, we can prove that other sets are countable or maybe not. What do you think in this case? A, is it countable or not? Can you define a bijective function from the set of natural numbers to the set A, or conversely, doesn't matter because f is one-to-one, so it doesn't matter who is the domain and the codomain. Of course we can. For example, f defined on the set of natural numbers taking values in n, f of n equals this. You see here, the basic fact is that n belongs to the set of natural numbers here. So this function is obviously a bijective map. It's a one-to-one map, and it's a bijective from the set of natural numbers to the set A. So obviously, it results that A is countable. Okay, so the proof is, if we know the definitions and the basic examples, things are very simple. If not, it's impossible. So I insist, you must learn the definitions for every notion. Don't start to solve exercises if you don't know what that means. What it means to be countable, what it means for a series to be convergent, what it means for, I don't know, power series to be convergent, and so on. So the basic notions must be known, their definitions. Okay, now we have also some basic examples of uncountable sets. So these are countable. Some basic examples of countable sets. We have also some basic examples of uncountable sets. The first example is the following. The set A, the set of all those elements of the following type, sequences or strings. These are called AJ belongs to 0, 1. Here is not important, it's 0 and 1. There are two different symbols. So the set of all these sequences of 0 and 1, we proved, you have the proof. You have the proof in the lecture that this is uncountable. And also, the main argument here is the so-called Cantor's diagonal argument. And you must know it to try to use it in some close examples. The other type of uncountable set is the every interval. The interval, for instance, 0, 1, the interval of real numbers between 0 and 1 is also uncountable, and you have a proof there in the lecture. You must know it, because in some other examples you must somehow use the same argument. Of course, because this interval is uncountable, the whole set of real numbers is uncountable. Yes, these are the two basic examples of uncountable set that you have in the lecture. So any other set which is somehow related, for example, if you take the set X of all those elements, so strings, with AJ belongs to, for instance, the set alpha, beta, and gamma. Of course, this is uncountable, and the argument is the same as here, but you must know it. Yes, the proof of this one is in the lecture. If you want, I can retake it, but I think it's a waste of time. It's already written. So for this one, it's also uncountable. Yeah. Okay. So here you may have an exercise for a set to recognize if it is countable or uncountable. Okay. Okay, when I refer to the partial, I mean for all the groups, not just the groups which will have the partial with me tomorrow. Also the other groups. The exercises are similar, and the chapters will be the same. So, okay. Of course, the exercises will be different. Okay, what we still have? Series, for example. Series of numbers. Here you must know how to prove, how to check that a series is convergent or divergent. And for that you have different tests of convergence. For example, if I take the series, for example, this one. And the question is if it is convergent or divergent. Or also we can add a question to be absolutely convergent, but we shall see here that in this case it's somehow elementary. So the question is if this set is convergent or not, convergent or divergent. Here you must recognize this is a classical example of the use of the so-called limit test with n at alpha. What the limit test with n at alpha said? If you have the series sum of a with an positive, so it applies only to series with positive terms. What the test says, if limit when n tends to infinity of n at alpha times an belongs to 0 infinity, so this limit exists, it's not 0 and it's not infinite. It's a number, it's a non-zero number. Then our series has the same nature as the series 1 over n at alpha, the so-called Riemann series. And don't forget, the nature of this series is known from the theory. this series is convergent if and only if alpha is strictly greater than 1. Okay, so the idea to apply the test is to find an alpha, a particular alpha, but an appropriate alpha, for which this limit is as it is written here. It's not 0 and not infinite. In that case, the exercise is over, because now then we know the nature of the series is the same as this series with the appropriate alpha we found. Now, in order to apply this test here, we need a small variation of the form of the sequence AN. You can see it is positive, that is obvious. But first of all, we shall amplify with the conjugate, because in this form it's a little bit difficult, because here you have infinite minus infinite, which is difficult to be computed. So if we amplify here by the conjugate of the numerator, above we shall get n plus 1 minus n, and below we shall get n times square root of n plus n plus 1 plus square root of n. So finally our series is this one. Now it's obvious it is a series of positive numbers, and all we have to do is to apply the previous test in this form. And now the question is, what value for alpha should we take in order to get a limit which is not 0 and not infinite? Please tell me the value for alpha, the appropriate value for alpha, for which the limit is non-zero and not infinite.
3 over 2.
3 over 2. Very well. Explain us how did you did compute it. So below is the power alpha, and sorry, above is alpha, and below what we have?
N times square root of
And at 3 over 2 times square root of 1 plus 1 over n plus 1, actually. Yes. So the idea is to take off as a common factor the greatest power of n. Here we have n at 1, and here we have n at 1 over 2. So finally, we have n. So this limit will be not 0 and finally when the powers are equal. So alpha must be 3 over 2. So if for alpha equals 3 over 2, this limit will be, here you simplify and you get what? 1 over 2. Which is indeed not 0, not infinite. So the exercise is over. Our series, this one, has the same nature as the Riemann series with alpha equals 3 over 2, with this one. And from the theory, we must know that this one is convergent or divergent. It's convergent. So our series will be convergent simply because it has the same nature as this one. Okay, so this technique, it's very simple, but you must know it. Amplification with a conjugate. Of course, if you have roots of order 3, you must somehow amplify with the appropriate conjugate, which is given by this formula: a equals a minus b times a squared plus ab plus b squared. So, for example, if we have sum of let's say square root of fn plus 1 over this one, for example, let's put it here 1. Same idea, we must, let's put it here, root of order 3. Yes? Same idea, but this time we need to amplify with the appropriate conjugate, which is this one. So here you'll have root of order 3 of n at 3 plus n at 2 plus 1 squared, this one, yes, plus n times root of order 3 of n at 3 plus n squared plus 1, and plus n squared. This is the conjugate of the denominator in this example. So we get sum of who? Below we shall have n at 3 plus n squared plus 1 minus n at 3, according to this formula. And above we shall have root of order n plus 1 times what? Times all this conjugate, all this expression, which must be written. Okay, and now the idea here is to use the same test with n at alpha. N at alpha times this one. I shall not write it anymore. It is this one. This is what I need to write here. And now tell me the good value for alpha for which the limit will be not zero, not attention. Here n at 3 and n at 3 will vanish. So this is actually what we have. So below we have n squared plus 1 and above we have all this. Okay, so what's the maximum power above? Yes, I'm listening.
N at 2 plus 1.
There will be n at 1 over 2 from here. Yes. And from the parenthesis, there will be n squared, if I see right. Times, you understand, here it's a lot to write. Okay, so now above we shall have the power alpha plus 5 over 2, which must be equal to n, which means alpha, it's a negative value. It's minus 1 over 2, which is anyway strictly less than 1. So our series will be divergent because it will have the same nature as the Riemann series with an alpha which is less than 1. Okay. So simple facts like this can solve a problem. So this is the test with n at alpha. Other test, we have ratio test or root test. Let's try one with the root test. For example, let's study the nature of the following series. Okay, so here, because of the expression, we must think to the so-called root test. What the root test says, it says if you have a series with positive terms, all the time they must be positive. We compute here the limit of root of order n of modulo of a, and if n is positive, we don't need the module, yes. Now, if this limit is less than 1, the series will be convergent. If the limit will be greater than 1, it will be divergent. And if it equals 1, actually the test doesn't decide the nature. We must look to another method, which will be more effective here, more appropriate. Okay, so why we must think to the root test? Because of the special form here. You have the power n, and when you apply the root test, you take the root of order n. So exactly what we need. So here we need to compute limit of root of order n of n plus 1 over 3n plus 1 at n, which means limit of n plus 1 over 3n plus 1. And this limit is equal to what? You don't know the limit, the value of this limit.
1 over 3.
It is 1 over 3 of I wait for you to answer because I also want to know exactly what you know and what you don't know. So it's 1 over 3, which is in 0 infinity. Sorry, which is, it is strictly less than 1. and it is less than, in case if the limit is strictly less than 1, the series will be convergent. So our series is convergent. If here the limit would be greater than 1, the series would be divergent, of course. So this is the root test. Okay. An example of the ratio test. This example of the ratio test. I shall clean up the whiteboard. Okay, the root test, for example, the ratio test. Let's consider the following. Okay, so obviously the sequence inside is positive, so one can apply the test for positive series. Here, this is not with root test. This one can be very simply written. This is with n at alpha test. One can write it like as follows: logarithm of n plus 1 over n over n. Yes. So the sequence an, it's logarithm of n plus 1 over n, everything over n. Okay, so now what test should we use? You see, this can be written as 1 over n times logarithm of 1 plus 1 over n. Yes? So this leads us to the following idea. We know a limit. Remember, there is a so-called fundamental limit which says that if xn is a sequence which tends to 0, then the sequence logarithm of 1 plus xn over xn, yes, tends to what? You know this limit? If x, it's 1. Very well. This is a fundamental limit. We must know it and apply in exercises. Okay, so this leads us, I think, to the idea to apply the limit test with n at alpha. More precisely, let's try to find alpha for which the following limit is not 0 and not infinite, as in the previous, and as in the first two examples. That means limit of n at alpha times 1 over n times logarithm of 1 plus 1 over n. Okay, so now if you use this limit, what's the appropriate value for alpha? Well, actually, we can write it like this: n at alpha times 1 over n times logarithm of 1 plus 1 over n. Here we need what below to have this limit?
1 over n.
1 over n. And we don't need to, and we have not to change the result. So we have to multiply by 1 over n. Yes? Okay? So this limit is 1, according to the previous fundamental limit. So we have a limit of n at alpha over n squared. What's the right value for alpha to get a non-zero and not infinite limit? If and only if alpha equals 2. So in this moment, we know that our series has the same nature as the corresponding Riemann series with alpha equals 2, which means this one. Well, and this one is, of course, convergent. So our series is convergent because for alpha equals 2, the Riemann series is convergent. Okay, if you have other questions here related to this example. So it is with n at alpha.
Would we have used the logarithmic test?
No, logarithmic text I shall not. Just the test we studied at the lecture. It's very well. It's very good to know it. Very well if you know it. But for the partial, I will not. I will consider up to the Rabe-Duhamel test. Okay, if you want to see something with parameter, for example, let's consider the following service. Here, A and B are both positive, and C, of course, is greater than 2. You see, these are the conditions to have a positive series. Okay, so A, B, and C are parameters, of course. And the question is the nature of this. So the sequence which defines the series, it is this one. Let's call it Xn. Now, the most appropriate test here seems to be the ratio test. The ratio test says the following. If you have a series with positive terms, and if L, which equals the limit of xn plus 1 over xn, is less than 1, then the series is convergent. If it is greater than 1, the series is divergent. And if the limit is 1, actually the test doesn't decide. We must go to look for another test, which will decide in this case. Okay, this is the ratio test. Now, ratio test is good when the sequence xn has a form which allows simplifications, of course. And in this case, because you need to simplify this ratio. So in this case, it seems to be appropriate. So we shall compute L as the limit of, here it's a little more complicated to write, it's more, but we shall write everything. So above we need to write xn plus 1. That means so instead of n, we put n plus 1, so we shall get a plus 1. Below we have b plus 1 times c minus 2 at n plus 1. This is xn plus 1. Now let's see who is an. Of course, an is what's written in the series. And times c minus 2 at n. And now we must somehow simplify here. We have a lot of simplifications. If you see, all this expression will be simplified with this one until a plus 1, which is the last factor here. But before a plus n, it was a plus n minus 1. The same for the products with b. Sorry, here b plus n still is still here. And of course, here we simplify by c minus 2 at n, and we get c minus. So after we simplify, we shall get a plus n over b plus n times c minus 2. Okay? And the limit is what? What's the value of this limit?
Minus 2.
It's c minus 2 because, of course, this ratio tends to 1. So the limit is c minus 2. According to the test, if c minus 2 is less than 1, then the series will be convergent. That means c less than 3. So if c is less than 3, our series will be convergent. If c minus 2 is greater than 1, our series will be divergent. So that means if c is greater than 3, our series will be divergent. Attention, whatever the values for A and B, of course, positive are. So actually, in most cases, it is simply C which decides. A and B seem to play no role in the convergence of the series. But we still have one case, if C equals 3. If C equals 3, the limit here will be 1, yes? So the test doesn't decide. We are in this case. So what we have need to see what happens if C equals 3? Okay, if C equals 3, our series will be this one. Okay. And now the question is how to decide the nature of the series, because the ratio test doesn't decide. Well, in the case when the ratio test doesn't decide, we go to the Rabe-Duhamel test. What the Rabe-Duhamel test says? It says the following. Here we need to compute the following limit: n times an over an plus 1 minus 1. And the answer is the following. If this limit is greater than 1, the series will be convergent. If the limit will be less than 1, it will be divergent. And if the limit is 1, the test doesn't decide. Now, so I advise you to apply first the ratio test. Don't go directly to Rabe-Duhamel test. So first apply ratio test, and if the ratio test doesn't decide, then go to Rabe-Duhamel test. So don't go directly to Rabe-Duhamel test. Okay, so let's apply Rabe-Duhamel test for this series. Okay, so now an over an plus 1, we can take it directly from above, but I shall make the computation from the very beginning. So an over an plus 1. I repeat, we can take it from above, but let's do it from the very beginning. Attention, here you see is the reverse of the ratio from the ratio test. It's an over an plus 1. Okay, minus 1. And here, of course, we have a lot of simplifications. So now we have n times, we have, of course, this one is not, it's b plus n over a plus n, negative 1, which means n times b plus n minus a minus n over a plus n, and with n vanished, so the limit is nb over n times b minus a over a plus n. Okay, and now limit. This limit equals what?
B minus A.
Very well. B minus A. So the conclusion, Rabe-Duhamel test, if B minus, attention, we are in the case when C equals 3. Otherwise, the nature was decided. If B minus A is greater than 1, our series will be convergent. If B minus A is less than 1, our series is divergent. And now we still have one case. What happens if B minus A equals 1? The Rabe-Duhamel test doesn't decide. But let's see what happens when B minus A equals 1. That means B equals A plus 1. Just replace in our series B equals A plus 1 and see what you get. So the series will be A times A plus 1 up to A plus N minus 1. And below you have B, which means A plus 1 times A plus 2 up to A plus N. So here you simplify by all this expression up to here, and you get sum of A over A plus N. And now this is the series we need to know the nature. What's the nature of this series? Because you can recognize it directly. We don't need.
It's divergent because it's I don't know how to say.
The Riemann is the sort of Riemann series. It's the harmonic series. Yes, we know sum of 1 over n. We know it's divergent, and this is, you can use the test with n at alpha for it, and compare with 1 over n. Yes, which is divergent, the so-called harmonic series. Yes.
But what if A is equal to 0?
A cannot be 0 because A is strictly greater than A and B are both greater than 0. Well, if A equals 0, you can see directly from this is the sum, it's 0, but it's not interesting. So A and B, remember the condition was like this. Where these were the conditions. So for every values of the parameters A, B, and C, now we know the nature. So for most of the cases, ratio test decided, unless C equals 3. For C equals 3, the ratio test doesn't decide. So we went further to Rabe-Duhamel test. And Rabe-Duhamel test gave us this result. Still, we have one case when the Rabe-Duhamel test didn't decide, when B equals A plus 1. And the nature now was decided directly from the series. This is the series, and obviously this is divergent. Okay. If you have any question here. So this is about series of numbers. Now, after a series of numbers, we have we still have power series, elementary functions, Taylor polynomials. Yes. Which topic do you want now to continue with? Please. To compute integrals with elementary functions. This is what you said?
Yes.
Okay, so let's compute integral from, let's say, 0 to 1 over 2 of sine of x minus x, or better, let's write it reversed. X minus sine of x over x dx. Okay, the idea here is to replace the complicated function like sine of x here with its power series. Of course, this integral can be written also as integral from 0 to 1 over 2 of 1 minus sinus of x over x. It's the same, but I shall prefer to take it as in this formula. So the problem is the sine of x anyway. If you take it like this or if you take it like that, it's the same. The problem is sine of x. So now we must know the power series of the definition, the power as a power series of sine of x. You must know it, or if you don't know it, you must know how to find it. But this is a little bit tricky for the sine of x. So I recommend that for the exam, you must know it by heart. You know in the lecture how we obtained it.
Defining it as the imaginary part of.
Yes, by using the exponential function, and we expand as e at ix. The real part is the cosine, and the imaginary part is the sine. Okay, very well. But I recommend you to know also by heart, because it may take you a few minutes to find the formula, and it's an advantage to know it by heart, and it's not complicated. This is the power series of sine of x. And now I want to write few terms here. Sorry, here okay, we can take it. We can put also here x squared. Put below, put x squared. So this one is no more valid. So take this one, x minus sine of x over x squared. It's more instructive. Okay, so I want to write few terms from the series of sine of x to understand better how it looks like. So when n equals 0, you get x. When n equals 1, you get, first of all, minus from this one. When n equals 1, here you get 1 over 3. Sorry, here is the factorial. It's minus 1 at n over 2n plus 1 factorial. Yes, I forgot to put n. Over 3 factorial. Yes, x at 3. Plus, when n equals 2, we shall get plus 1 over 5 factorial x at 5, and so on. Yes, so actually we have only odd powers, and below we have the factorials, and also the sign is alternating. Okay, now what we have to do here is the following: to subtract from x sine of x of this series. So x minus sine of x will be x minus all this sum. And so on. So what do we get? As you can see here, the first two terms will vanish. So we get 1 over 3 factorial x at 3 minus 1 over 5 factorial x at 5, and so on. So this is the numerator, x minus sine of x, which can be written as sum when n is greater or equal than 2 of x at 2n plus 1. Yeah? And now below we have 2n plus 1 factorial. What we have above? The sign is minus 1 at n minus 1. Because you see, when you put n equals 1, you get plus. When you put n equals 2, you get minus. So, of course, the sign changed. Why? Because we had this minus in front of the series. So this is the numerator. Like this or like that is the same. The numerator of our ratio. We need to integrate x minus sine of x. And now we need to divide by x squared. Yes? You see, the ratio, the series starts with x at 3. So we shall simplify by x at 2. If you want, you can take off x at 3 even. But anyway, we can simplify by x at 2 because here the least power is x at 3. So finally, our integral will be integral from 0 to 1 over 2 of what? If we simplify here by x at 2, we shall get x at what? We simplify by x at 2. So it will give us x at 2n minus 1. And when n equals 2, you get x at 1, which is okay because it started with x at 3. We divided by x at 2. So the first term will be x at 1, which is okay here. So this is the integral we need to compute. Attention, to approximate. Actually, I shall... and now, what we do is to integrate term by term this power series. That will be all the constants go outside the integral, and what we need to integrate, n minus 1, integral from 0 to 1 over 2, x at 2n minus 1 dx. Okay? The primitive of x at 2n minus 1. The primitive of x at 2n minus 1 is x at 2n over 2n, between 0 and 1 over 2. Here is the factorial. So it gives us times, here be 2n, and times, you have here 2 at 2n. Okay, so what we did until now is the following. We proved that the exact value of this integral equals the sum of this series. I shall write it again to see it better. Times 2n times 2 at 2n. Okay. I want to know if this result is clear, how we obtained it. So first we replaced sine of x by its power series, then we made the computations here, like this. Then we divided by x at 4 and we simplified by x at 2, sorry. We simplified by x at 2. And finally what we did here was simply to integrate, the only integral we need to compute is this one, which is the simplest integral as possible because it is a power. We compute this integral and it gives us this one, or actually 1 over 2n, this one, times 2 at 2n. So I repeat, do you have any question about how we obtained this formula? So what we did is to obtain the exact value of the integral as the sum of this series of numbers. So the sum of the series equals the value of the integral. And now
I have a question.
Please.
Could we also start the sum from 0 and have n plus 1 instead of n? Like replace n with n plus 1?
Yes, of course. I agree
Okay.
with. Yes, you can write the sum with, start with 0, but then instead of n, you must put n plus 1. It's okay. It's the same.
Okay, thank you.
Okay. Okay, so, and now the question of the exercise was it was given this integral. What to do with it? The question is this: approximate the integral with an error. General, let's call it epsilon. In our case, let's say epsilon must be less than 10 at minus 3, for example. Yes, this is, so our exercise is the following. Given this integral, approximate the value of the integral with an error less than some epsilon arbitrary, but in our case we shall take it to be 10 at minus 3, but we shall discuss also the general error. We will do it after the break.